Hi, this is Mark Maney here. I've just got a couple of videos which are going to outline how to sketch exponential functions. So exponential functions, one of the whole range of functions that we're going to look at through the course of Math Methods course, is typified by either increased growth, and that is growth on growth, where instead of increasing by a certain amount for every interval that we move along the x-axis, and that amount being fixed, we increase by a rate. So just to illustrate that, we might increase by a rate of 100%. So as we move along, if initially we started with 1 unit, as we move along the x-axis, that doubles, 100% being a doubling effectively. So our 1 value then goes to a 2, and then as we move another step along the x-axis, it will double again to 4, and another step sees a doubling, further doubling to 8, and another step to 16. And you can see very quickly that we're actually going up quite steeply. So typically it's written in this form, where the x is the independent variable and the y is the dependent variable, and this value a is known as the base, and the base will change depending on the problem that you're being given, and also the rate at which we are moving along, whether we're doubling or whatever. Okay, so what does it look like and how do we actually graph these things? So let's have a look. We will actually look at doing something, and I'll look at a very basic graph. So we might look at sketching, say, something like y equals 2 to the power x, and have a look and see how that would actually work. Now the 2 here is an example of that doubling effect that I spoke of earlier, where if we started at the point x is 0, we could expect that y would equal 2 to the power 0, and as we know, 2 to the power 0, or anything to the power 0, would be 1. So when x is 0, y gives us a value of 1. So we've located there what's called the Y-intercept, and it's going along that way. We typically need at least 2 points on our graph. Importantly for exponential graphs, and typical of an exponential graph in the most basic form such as this, not only do we need those 2 points, but we need to locate something called the asymptote. Now the asymptote is a horizontal line where the graph will actually approach but never cross. And our asymptote here is located along the x-axis, and that's standard. And so there's a few things that we can do. Firstly, we'll mark in that asymptote, and typically it's done with a dashed line, just to indicate that this is the line that is not to be crossed over. And as I said, for this one, it coincides with the x-axis. Later we'll see examples where the asymptote shifted, as is the rest of the graph. So we've located a point here. We've already discussed the fact that as we go along, the shape of the x-graph increases, and it increases in proportion to what's gone before. So we very quickly get a growth in it that looks something like that. And that can be extrapolated backwards. And we see that the graph approaches our x-axis and the asymptote that lies on it, but never ever touches it. Okay, theoretically at least, it will continue on to negative infinity there without ever actually touching the x-axis, but getting closer and closer as we go along. Now just a few things, and I've noted them here. So as you sketch an exponential graph, you do need to mark in the asymptote and locate it. It is a horizontal line in an exponential graph, typically situated along the x-axis. Later on we'll see where and how that shifts. You locate the y-axis intercept, which we've done already, and we mark it in. So I'll place that at 1. And then you locate any x-axis intercepts. Now already I've said to you that this asymptote means that there will be no opportunity for the graph to actually touch the x-axis. So in this instance, there won't be any intercepts for it. So we have to choose another point. So typically on any graph, including these exponential ones, we'll ensure that we have 2 points. The y-intercept typically, and one other. Now the easiest one to locate, or often the easiest one to locate, is when we just let x equal 1. So I'm going to replace x with the value 1, and we've got 2 to the value 1, and add 2 to the power 1, which is just 2. So you can see perhaps why the value of 1 is often chosen. because they're very easy to calculate. So if we go 1 across, we've now gone to 2 up. Typical, as I said, of that doubling that occurred previously. So marking that in, and then sketch a graph which joins those 2 points and approaches the asymptote but doesn't actually touch it, with a nice smooth sweeping curve. And that's it for that one. I'll show another example that hopefully will just reinforce the idea of what we've done. And this is example 1. So in example 1 here, again, we've got a typical, just to focus here, a typical exponential function, and these are easy to spot. Okay, we've got the two variables, the independent and the dependent variable, and the independent variable is actually, let me just see if I can do that. The independent variable is actually raised as an indice or an exponent. Okay, the term exponent is used there. Rightio, so to sketch it, we locate the asymptote. So at this stage, our asymptote has not moved, and I'll show you in a second example or another example where that might occur. But we locate the asymptote, which in this instance, the asymptote is unchanged and is at y equals 0. So that's our asymptote. It's often a good idea to note it. Next thing we do, sorry, having trouble with this on this. Next thing we do is actually try and locate the y-axis. So our y, or the y-axis intercept, and we know that that occurs when the value of x equals 0. And so we will substitute and replace x with the value 0, and 4 to the power 0 is 1. So our y-intercept, my apologies, that's changing again, y-intercept is 0 at 1. Okay, now I've already said we've got an asymptote at y equals 0, so that automatically tells me that in fact we are not going to have our graph go through and touch this x-axis. So there's no point actually going along and trying to find this y-intercept because it doesn't exist. So we'll mark in our asymptote then. There's our x-axis. I'm also going to put y equals 0, which I perhaps should have done previously for the previous example. So there's y equals 0. And having marked that in, we can now search for a second point. So again, any other point's fine. There's our first point at y equals 1. And so we'll choose another point. And typically we just locate it as a second point on the graph. And I'll choose x equals 1 just for ease. So my y-intercept and that second point. So y equals 4 to the power 1, which is of course 4, and that provides my second point here. So here, for this graph, we go across 1 and up 4. Mark that point in. Okay, and we sketch our graph so that a nice smooth sweeping curve passes through both of those points with arrows on either end, again showing that our line down here approaches but doesn't ever touch that the asymptote that falls along the x-axis. Okay, you might notice in comparison to my previous graph that this one is rising a bit sharper. We're actually looking at a 300% increase here, relatively large increase in comparison to the other, and that's all adjusted according to this base. So we're seeing that this is actually rising relatively quickly. Okay, so I'll pause this video. You might like to check out the next video, which shows a few more complex examples. I hope this has helped, however.